So in this video, we're going to be looking at halogenation as a reaction in organic chemistry, as well as how we can actually draw a free radical substitution reaction mechanism. Now, halogenation is going to be when we take some sort of an organic compound and we react it with a halogen to form some sort of a haloalkane. Now, in this example, we're going to be looking at taking something like an alkane, reacting it with a halogen to form a haloalkane. And basically, all that we're doing is we're taking some sort of a carbon-hydrogen bond and we're swapping out the hydrogen in this reaction to actually form a carbon-halogen bond where X is represented by the general halogen. That could be anything like chlorine, bromine, iodine, and so on. Now, if you were to look at the conditions of this reaction when dealing with alkanes, we need UV and high temperature. Now, the reasons that we need these conditions is because we want to generate something called radicals from our halogens, because alkanes generally, they're going to be quite unreactive to a broad range of chemicals. That's why we tend to just use them as fuels. Now, we said they're unreactive. Remember why? Because of course we've got carbon-hydrogen, carbon-carbon bonds with high bond enthalpies. They're going to be very strong, and also they're going to be non-polar molecules as well. Now, of course, the reaction conditions we need to remember: UV, high temperature, and we need to think about this example over here. We've got the halogenation of propane, where we take a molecule of propane which looks like this in structural formula, we react it with something like chlorine, and we end up forming, in this case, 1-chloropropane and a byproduct which is going to be HCl. Now, I can also write this out as a synthesis pathway, and a synthesis pathway is basically to show how a reaction goes from reactants to products with our conditions given above the arrow, which you can see is going to be UV and high temperature again. I've got here a molecule of propane, reacts with chlorine, we end up producing 1-chloropropane and then HCl. Now, the name of the actual mechanism is going to be free radical substitution, where we end up producing, of course, a haloalkane from an alkane, or we end up swapping, that's why it's called substitution, a hydrogen on one of the actual carbon atoms for a chlorine instead. And that's basically what's happened. The chlorine and the actual hydrogen has actually swapped places, and we actually end up with 1-chloropropane here and then HCl as well. Now, if we look at this process, it happens in 3 steps. It happens in terms of initiation, propagation, and then termination. Initiation is going to be when our radicals are going to be made in the first place. Propagation is when we take these radicals, we react them together to use them up and make even more radicals. And then termination is when the reaction stops and our 2 radicals, any combination, they combine together to make a neutral molecule overall. So yeah, just to be clear, the halogenation is going to be the reaction name, and then of course the reaction mechanism is going to be free radical substitution. Now, if I were to look at an example of this, I've got methane that reacts with chlorine by radical substitution. We're already told over here, but a key hint is we're taking a carbon-hydrogen bond, we're replacing the hydrogen with something like a halogen, like chlorine, bromine, or iodine, or whatever it might be, but it has to be a halogen. Now, if we're asked to describe fully with equations the mechanism for this reaction, we need to be able to show all possible termination steps, our propagation steps, and then of course our initiation step as well. You can see over here I've got methane reacts with chlorine in our overall equation, and we end up forming chloromethane and then HCl. This hydrogen has swapped out with this chlorine from what we can see, of course, in this reaction between chlorine and methane itself. Now, if I were to look at my initiation step, this is when our radicals are going to be made in the first place. It's the start of the chain reaction, and we actually end up taking a molecule of chlorine. We take, of course, the conditions of UV and high temperature, where we put UV above the arrow. We end up with homolytic fission taking place. The covalent bond between the chlorine atoms breaks. 1 electron goes to each atom, forming 2 radical species. And that's what I've got over here. And I'm going to show it's a radical by, of course, showing a big fat dot. Remember, it's called free radical substitution. Substitution, you're swapping one atom or group out for another. Radical, because it involves radicals. Now, what's going to happen next over here? Well, remember, alkanes are unreactive. The only way to react them is, of course, to react it with something that's going to be very reactive. So what I can actually take is my chlorine radical over here. That's going to react with, of course, our methane radical. Remember the purpose of the propagation step. We're trying to take our radicals, react it with, of course, neutral molecules to make even more radicals. In this case over here, I end up making a methane radical, because what actually happens is that chlorine radical actually strips off one of the hydrogens in methane. That makes a methane radical, and then it also makes HCl as well. Now if I were to look at this, basically what I've got is methane as a molecule, and we actually end up losing, right, one of the hydrogens that undergoes homolytic fission, and we actually end up with this carbon here having an unpaired electron. That's what makes it a radical. That's what makes it very reactive. Now we need to be able to show, of course, this methane radical, of course, continuing this chain reaction, because that's what it is, and that reacts with a neutral molecule of chlorine, and what we actually end up making is of course a molecule of CH3Cl. That's going to be chloromethane, and then we also end up making a chlorine radical. Now this chlorine radical here is going to carry on reacting in this first step over here, and of course this is going to be a chain reaction that generates loads of methane radicals, loads of chlorine radicals as well. The reaction only really stops when we reach our termination step, where two radicals come into contact with each other and they end up forming a bond between each other, making a neutral molecule overall. There's different combinations that we can get, because remember what we said, we've got loads of chlorine radicals, loads of methane radicals. Now the first combination that we can actually get is when we take two chlorine radicals and they of course come into contact with each other and they end up forming a covalent bond to reform the chlorine molecule itself as well. If I were to look at this, I've got two chlorine radicals, one here, I'm going to flip the other one over here. If they form a shared pair of electrons with this chlorine radical here, this chlorine radical over here, we actually end up with a neutral molecule of chlorine. That's our first termination step done. What about another combination? Well, I can actually take this methane radical over here, take another methane radical where I flip it. Now remember, these two electrons, they can form a shared pair of electrons, where we actually end up with, of course, a covalent bond between these two, and if you name it, it ends up being ethane itself. So I can take two lots, and then I'm going to show the actual radical again. Remember, the reason why I put the radical next to the carbon in this case is because, of course, that's where the radical is going to be. I'm going to end up with two lots of methane radicals. They're going to, of course, react together, and we end up forming a molecule of ethane, which looks like this. Now our final termination step is when we take, of course, our methane radical, and that's going to go ahead and that's going to react with, of course, our chlorine radical, and that's what actually makes our desired product that we want. That's shown over here, CH3Cl. We end up with chlorine as a radical, and what we end up with is a shared pair of electrons with these two radical species, and that actually makes a molecule of chloromethane. So we end up with, of course, a chlorine radical that's going to react with our methane radical over here, and we end up forming, of course, chloromethane, which is CH3 and then Cl. Now in the exam, you actually get 6 marks for this question, 1 mark for the initiation step, 2 marks for the propagation steps, and then 3 marks for all of the actual termination steps as well. It's a very common question that comes up next every year on the exam that we need to get familiar with. So yeah, I've got a task for you to try. Feel free to pause the video on this slightly easier example with some blanks. Resume once you're ready to go over the answers. So yeah, in this case, we've got methane that reacts with bromine by radical substitution. So we know, of course, that's our reaction mechanism, because there's lots of different types of reaction mechanisms you're going to deal with in A-level chemistry. We're asked to complete the mechanism for the following reaction. Now we can see here we've got methane reacting with bromine this time to give us bromomethane and HBr. It's going to be the same as our worked example, where of course we end up with our initiation step. So we put UV above the arrow, and then we end up with 2 bromine radicals being formed. There's our homolytic fission taking place. We end up with our propagation step next. That's when, of course, our bromine radical is going to react with a neutral molecule like methane to make it very reactive. We end up losing a hydrogen there, and then we end up forming, of course, HBr as well. And then, of course, we need to show the examiner this is a chain reaction where the methane radical reacts with something like, let's say, a neutral molecule of bromine to show it's a chain reaction again, and we end up forming bromomethane, and then, of course, we end up with a bromine radical. This bromine radical is going to be recycled, and it continues on the chain reaction. Now the termination step is going to be, of course, when the reaction stops, where we take 2 radicals, react them together to make a neutral molecule. In this case, we've got a methane radical, bromine radical, that together makes, of course, bromomethane. The next step, of course, we've got an ethane radical being formed. What must we have had? Well, it's going to be 2 lots of, in this case, it's going to be methane radicals. So I react them together and I make the neutral molecule, the non-polar molecule, which is going to be, of course, ethane. The next one, we're going to have 2 lots of bromine radicals. They can come into contact with each other, and we can actually end up with, of course, a neutral molecule of bromine. Now that that's done, I've got a more challenging example for you to try. I've got here a molecule of ethane, chloroethane, that's going to be formed from ethane. I want you to show the position of the actual radical, which carbon atom it's going to be on, by putting it above the actual carbon atom itself. Pause the video, have a look at the following question, resume once you're ready to go over the answers. So yeah, looking at this one over here, we're told ethane in this case is going to react with chlorine by radical substitution. We need to describe fully with equations the mechanism for this reaction, showing all possible termination steps using structural formula only. Now the first one is going to be quite easy. We've got initiation taking place. We're dealing with chlorine. Make sure you don't get that confused where you accidentally put bromine down, because it does happen to quite a lot of people. Now in this case, we end up with, of course, chlorine that undergoes homolytic fission, where we end up with, of course, UV above the arrow, and then we end up forming our 2 chlorine radicals. That's 1 mark for the first step so far. Now the next step is the propagation step, where we take our chlorine radical, our highly reactive species with an unpaired electron, and that's going to react with our unreactive ethane molecule. Remember why this happens, because ethane's unreactive. We need to react it with something that's very reactive to balance it out, and we end up producing, of course, our ethane radical, where I'm going to put CH3, and then I'm going to get rid of one of the hydrogens because it's been nabbed off by the actual chlorine radical itself. Now don't forget, we need to put a radical on one of these carbon atoms. It's going to be this one over here, because that's where I've removed the hydrogen from. There's our first propagation step done. What about the next one? Well, I'm going to show this as a chain reaction by taking my ethane radical. Again, we're using structural formula, so I'm going to show the position of the actual radical itself, and that's going to react with a neutral molecule like chlorine, and I end up producing, in this case, it's going to be chloroethane, where I don't need to highlight the position. It's just going to be called chloroethane on its own. I end up producing, of course, my chlorine radical, and that's going to continue to react on in my first propagation step. It's a chain reaction, and it's going to continue up until I reach my termination step. Now let's say if I were to look at my termination steps, right here we're trying to form chloroethane, and remember there's 2 of the possible ones that you can get. Well, termination step, the first one is going to be quite easy. I can take my 2 chlorine radicals, and I can actually end up forming my neutral molecule of chlorine. That's the first one done. The next one is a trickier one, because I'm taking 2 ethane radicals, which is going to be CH3, CH2. I'm going to put the dot above the carbon over here, and I end up actually forming a molecule that's going to be butane. Now, how have I actually figured that out? Well, what I like to do is I like to draw out the structure, or you can leave it in structural formula, but I like to flip one of the actual molecules. Now, let's see if I've got over here a radical of ethane. I have another radical of ethane over here, and I end up actually forming the shared pair of electrons between the 2, right? I actually end up forming a bond between carbon 1 and carbon 2 over here, this carbon over here and this carbon over here, and that bond means I've got 4 carbon atoms in a row, so I end up with 1, 2, 3, 4 carbon atoms, and that actually makes butane itself. So yeah, I end up making butane. You can see I've formed a bond using the 2 radical species. What about the next one? The next one's quite easy. We actually end up with CH3, CH2, and then a radical above this carbon atom over here, and of course we're told the product over here, so it's going to be chlorine radical that reacts, and we end up producing, of course, chloroethane. So yeah, there's our final product over there. You could have used molecular formula as well, but in this case I'm going to use structural formula because the examiners asked me to, and there's that last one done there. Now, another way that the examiner can actually ask you to do this is to do it in skeletal or displayed formula, which you can use either one in this case, but this question is asking for skeletal formula. Pause the video, have a go, resume once you're ready to go over the answers. So yeah, we're told over here that propane, that's going to react with chlorine by radical substitution, and we're asked to describe fully with equations the mechanism for this actual reaction, showing all possible termination steps with skeletal structures for organic compounds. Now the overall equation is given to us over here, and we've got UV high temperatures conditions, and if you were to number your carbon atoms as 1, 2, 3, you can actually see that the chlorine is swapping out with the hydrogen on the 3 position. The positioning is going to be very important in this example question. Now again, we need to show the skeletal formula structure, and that's going to be for our organic compounds only. We don't need to worry about things like chlorine. But yeah, the first equation is initiation. Our radicals are going to be made. We end up with homolytic fission. I form 2 chlorine radicals over here, UV above the arrow. That's our first step done. Propagation, we're going to take our neutral molecule of propane in this case, we're going to react it with our highly reactive species of a chlorine radical, and then we end up forming our product, which in this case is going to be our propane radical, and this dot is going to be next to this carbon atom over here because that's where our chlorine is going to join onto. And then we also end up forming, of course, HCl as well. There's our first propagation step done. What about the next propagation step? Well, I take my propane radical in this case, I end up reacting it with a neutral molecule of chlorine. We're going to show it's a chain reaction. We end up producing 1-chloropropane, and then we also end up with a chlorine radical as well, which we know goes on to react even further with another molecule of propane. Now in our termination step, we're going to get 3 combinations. The easiest one is going to be 2 chlorine radicals react together and we end up reforming our chlorine molecule. The next one is of course we take our propane radical and we react that with of course a chlorine radical, and we end up making the neutral molecule that we're after, which is going to be of course 1-chloropropane. Our last one's going to be quite tricky because of course we're going to take 2 propane radicals. You can just write it as an equation where you've got propane radical and then a 2 next to it, but what I'm going to do is to show how this bond is actually formed, I'm going to take of course a propane radical which looks like this, flip another propane radical which looks like this, and I'm going to end up with of course 1, 2, 3 carbon atoms here, 1, 2, 3 carbon atoms over here, and it's going to be this carbon atom that forms a bond to this one, and what we actually end up with is 6 carbon atoms long carbon chain. So I end up with of course 2 lots of propane radicals. They're going to react together and we actually end up forming a hexane radical, which is going to look something like this. I've got 1, 2, 3, then I've got 4, 5, and then 6 carbon atoms all together. So yeah, you can see I've got here my final product, my final termination step, and I'm just going to make this dot a bit more fat, and then this one as well, just to make it clear it's a radical and not something like a pen smudge or something like that. Again, you've got a 6-mark question over here, nice and easy. If you actually learn your steps inside out, it's the same thing over and over again. It doesn't have to be an alkane, could be anything really. So yeah, there's our final reaction mechanism done. Now there's some limitations when it comes to free radical substitution. Let's say if I were to take something like methane and I wanted to make something like chloromethane, and that was my target molecule that I wanted to make in industry, for whatever reason, I end up with a balanced equation that looks something like this. Now a problem with this reaction is going to be, of course, we can't actually control it that well, and we can actually end up with further substitution occurring. Now this is the reaction that we're after. This is the molecule that we're trying to produce, but let's say if another chlorine radical comes into contact with chloromethane, we can actually end up forming dichloromethane. If it was 2 more, we can end up forming trichloromethane. 3 more, we can actually end up forming tetrachloromethane. So it's going to be quite hard to produce a consistent product of chloromethane, a pure product of chloromethane, because we can actually end up with more substitutions taking place. Now one way to overcome this is to use an excess amount of our alkane. So that means that the chance of another chlorine radical coming along to do substitution again is going to be of course lower, right? Can't actually guarantee that you're going to make chloromethane, but again, you know, it's a problem with this reaction. Now another issue is that we can actually end up with substitution occurring at a different position along the carbon chain, and that results in isomers being formed, because although in our previous reaction we wanted to produce 1-chloropropane, there's nothing stopping another hydrogen atom being substituted for a chlorine at a different carbon atom along the carbon chain, forming something like 2-chloropropane. So there's our 2 limitations with this reaction. Further substitution can occur, and substitution occurs at a different position along the carbon chain, and that results in isomers being formed.